This video is a summary of the current source high-frequency AC link inverter project. Traditionally, high-frequency link inverters are voltage-sourced, have a full bridge rectifier, have large capacitors, and have large transformers. Our project would eliminate the use of such things. Our project goal is to develop a prototype that will allow us to test and validate a newly developed PWM and commutation methodology that aims to construct a high-frequency link current source inverter. There has been a great deal of investigation and design in high-frequency link voltage source inverters already, so our approach will be to provide an efficient solution to delivering power from increasingly demanded current sources, specifically solar panels. The inverter is designed to output a 60 Hz sinusoidal wave so that the model can eventually be improved to seamlessly connect to the power grid or provide an alternative solution to uninterruptible power supplies. The analytical data from our prototype will provide valuable feedback to researchers and support their efforts to make this unique approach valuable to industry. This is a general overview of the inverter. This schematic illustrates the gate drivers for the thyristors. Each gate driver controls two switches. This schematic illustrates the switches and the load on the secondary side. As you can see, there are 8 switches on the secondary side. The state machine is responsible for determining the gates and switching from positive to negative voltage. This is the output of the state machine on a scope, followed by the scope of the PWMs that serves as inputs to the state machine. The next part of the project was building and testing the analog components. The first PCB shown is the gate drivers for the primary side. At first, we had a lot of problems combining the thyristors with the gate drivers, so they were printed on separate boards for easier testing. This scope reading shows the gate drivers successfully switching on and off. Eventually, the thyristors worked as expected and the PCB was printed and tested. These are the gate signals to the primary side thyristors. After both the gate drivers and the thyristors were tested and validated, we combined the two processes and confirmed that they worked as intended. The scope shows that the voltage on the load is properly switching. Next, the secondary side was printed and tested. This was very similar to the building and the testing of the primary side, so this process did not take as long as the primary side. The problems for the project really started appearing when we attempted to combine the primary and the secondary side. After many days of testing, we figured out that our problem was that our current source was non-ideal and therefore the thyristors had a delay when communicating with the FPGA board. This caused them to not respond because of improper commutation of the thyristors was not allowing them to be turned off, and then they were stuck on. This flaw proved to be fatal for the project, and we had to switch from thyristors to MOSFETs for the primary side to allow us to make sure the thyristors could turn off. The next part of the project was the voltage sensor. The voltage sensor's main task is to send a signal to the FPGA board when the voltage across the load is about to go from positive to negative and vice versa. The FPGA then goes into the negative side of the state machine until it gets another signal from the voltage sensor. This simulation file shows how the voltage sensor works. The input voltage is the sine wave and the output voltage is the square wave. Once the input voltage is in between plus and minus 0.1 volts, the sensor sends a high signal to the FPGA board. The scope matches the simulation perfectly. This shows the entire system together. The parts on the breadboard make up the filtering part of the inverter. The filtering would prove to be the most frustrating part of the project. Here are some examples of outputs that we were seeing over the load. It is clear that there is a sinusoidal imprint on the waveforms, however, there is a lot of noise. In fact, the clear sine wave that you can see is 60 Hz, while the noise is 2 kHz, the second harmonic of the primary side. This led us to believe that the filter that we were using was not effective. We tried using many different combinations of capacitance and resistance. We also tried changing the code and changed the input frequency. Each change changed our output signal, but not in traceable ways. Eventually, after enough trial and error, progress was made. The first picture shows the two positive states across the load. The second picture shows the negative state. Combining these two is just a matter of utilizing the sensor to switch from positive to negative and then back again. This is what the signal looks like when the state machine is used to combine the signals. The changes that were made include the following: changing the primary frequency from 1 kHz to 10 kHz, increasing the capacitance to 116 microfarads, increasing the resistance from 20 ohms to 1 kiloohms, along with decreasing the input current from 1 amp to 700 microamps. While there is still some noise at the peak voltages on the sine wave, we can clearly see the sine wave, which was the goal of our project. This gives researchers a solid foothold to continue researching this technology in the future. The main drawback of our project was that we weren't able to use transistors on the primary side because of a lack of a current source. With a true current source, this wouldn't be a problem. Thank you for your time.